If I get it, I'll email you. In replacement for that, when I finish here and also tomorrow, I'll be happy to work through any of the homework problems. Or at the very least, what I'll do is set it up and show you how to do any of the homework problems you might have questions about. Okay? So the short answer was no. Okay. This is probably, I'm thinking, you can't see below this line?
It just depends where on the board.
Yeah, okay. All right, I'm not going to use this board, so I'm going to go back over here.
He's leaving the math up. Yay. No one can see the math anyway, so who cares?
In my opinion, this is probably, aside from the special functions, what I've written here is what you might put, oh, maybe I told you this or not, what you might put on your notes sheet for the examination. All right? So you will have for use at the examination one sheet of 8.5 by 11 paper, both sides, printed or written in any way you want. So if you want to, sort of photocopy the book and minify it onto a sheet of paper and then come in with a microscope, it's okay with me. You just have to put it, I don't want you to have a searchable thing. So you can't have it electronically, and if you had your computers, then unfortunately for me, you'd be able to communicate with one another, and I wouldn't know how to block you from doing that. And communicate with, like, Evan Weinberg or Joe Packey. So I can't allow you to have your computers. But one sheet of 8.5 by 11 paper, both sides, and a mathematical handbook.
So then no scanning tunneling electron microscopes?
It's fine with me.
But most of them are computerized.
Well, I mean, you're allowed to use it as long as you can use it without a computer.
As long as you can prove that it's a closed system.
So my experience is that just putting down the essence of what you need is best, because if you start packing stuff onto the page, you discover that you can't find what you need when you need it. All right, Evan, you had a comment, question? I thought I saw your hand. No? Okay. All right. So,
Ryan. So in future exams, will the same requirement be one sheet?
One sheet.
For each exam, including the final?
No. Final, you can have 3 sheets.
So it's not
I just changed my mind.
So it's not going to be 1, 2, 3, and then 3.
It could be
3 exams.
1 sheet, 2 sheet, 3 sheet.
Right, the idea is,
can you say, can it be cumulative for the future examinations?
Right. That was my kind of request. Because if it's not, then it's really ideal to use only 2/3 of a sheet for this exam. But you actually, then you keep writing another 2/3.
So someone's going to have to, more than one person in the class is going to have to email me to remind me that I just decided this. And that is that for the first exam you get 1 sheet. For the second exam you get 2.
Is it going to be cumulative?
For the third exam you get 3. And the final is comprehensive or cumulative.
The third exam is the final.
You only have 2 exams in the final. So
is that true?
Yes.
Okay, then for the first exam you get 1 sheet. For the second exam you get 2. And for the final you get 3.
And I have that on video.
Okay? What?
But the final's 2 exams.
And for the final, you get 3. And that's it. That should be plenty.
yeah.
I have an irrelevant story about myself here. Yay! No, don't turn it. It's okay. That is that was sort of the rule that they had at University of Chicago as far as the graduate qualifying examination was concerned. You were allowed 1 sheet of paper for, actually that was for the whole examination. It was an 18-hour examination, and in 6 parts. But it was an 18-hour exam. What you did was you filed your piece of paper with them, and then you'd come back and you'd get your piece of paper. So that was it. You just allowed 1 piece of paper. And I started and it's on everything that you supposedly learned as an undergraduate. So I started writing very, very tiny and trying to fit everything on the page, right? And I ended up filling 2/3 of the front of a sheet of paper, and then there was nothing else that I knew that I needed to put on the piece of paper. And in fact, I never referred to it, as most of you know. When you write a note sheet for an examination, most of the time you don't use the note sheet. You look at the note sheet when you don't know how to solve a problem, but it doesn't help you. And in this case, I'd say, well, although the math handbook is really all that you need in order to find the functions that you need. But sometimes writing out the solution of Laplace's equation in each of the 3 coordinate systems, well, actually be 4 special coordinate systems, spherical with azimuthal symmetry and without azimuthal symmetry. Writing it out for yourself rather than resorting to Schaum's, which gives you a generalized solution. They just tell you how the coordinates relate to one another, and then you have to plug them in to figure out what the Laplacian actually is. You don't want to do that. So the crib sheet, notes sheet, could be good for that sort of thing, but for the rest of it, not so much. For me, I need it for what I'm about to write down. I wrote down some boundary conditions here. Oh, I chose a good place to do this. Right? And these boundary conditions change when you have a dielectric in the problem. Right? But what? But they change, I think, in sensible ways. That if you remember the boundary conditions for problems with dielectrics, then you don't need to remember those anymore. Right? So there really would be only one set. All right. So first thing that we're going to do when we put dielectrics into a problem is define a completely fictitious and non-physical field. I want to repeat, it's fictitious, it's a mathematical construct that makes things easier. It's not measurable. And that's this. The D field, yes.
Then isn't the B field non-physical since the H one's one?
We'll come to that later. But yes. I'm going to define the relationship between this fictitious field, the D field, sometimes called the displacement field, and the electric field to be that, where this is the dielectric constant, or in DC, or dielectric function of a material. It is a tensor, but we're going to take it to be isotropic. All right, and linear. And I'll write this as well. I'll define one additional field. The polarization field. And so I could write the polarization field as the difference between the electric and the... I will.
Homework.
Do the trivial thing. Let's see, I got a sign wrong here.
No.
There.
Your sign was right.
Your sign
It was
was
right
right
before?
Yes.
Okay.
Do we need subtraction?
D minus E is equal to, yes. I wouldn't waste space on my crib sheet for that, right? But I'm doing that for a reason, and that's because it's directly relevant to the homework that is due on Thursday. And I'd be happy to answer questions and perhaps discuss that homework. Are you scratching, or are you, okay. All right, so I defined this new thing here, right? This fictitious field, the D field, is taken to be only due to the free charge in a problem. Okay? I talked a little bit about the polarization field. The polarization field arises from the polarization of atoms. You're not actually separating charge and moving them around over macroscopic distances. What you're doing is you're taking an atom that might have had an electric field built in, a polarization field in some direction, and you're rotating it a little bit, or you're taking the electron and proton that are in a problem and nucleus that are in an atom, and you're splitting them apart a tiny bit. But you're moving the charge itself over atomic scale distances. You're not actually moving it macroscopically through the material. So when charge moves over macroscopic distances, then we call it free charge. And the definition of macroscopic can depend upon
Scale you're looking
the
at.
scale of the problem that you're trying to solve, right? If you're concerned with the electric field over the size of this room, it may be that macroscopic, as far as we're concerned, we could have the room filled with, not touching, but if we had little metal spheres all over the place, if those spheres were like marbles, then we could treat them as fixed charge, right? But if we're worried about the field right near the surface of one of the marbles, then we're going to treat it as a mobile charge. Metal marbles, conducting marbles. So,
That would be a little problem.
the polarization field arises from charge that's only moving a very, very short distance. And the D field, the displacement field, which is a fictitious field that doesn't exist, obeys this. Relationship. The electric field is the result of all charge in the problem. Polarization is the sum of, well, let me put it a different way. It's the result of bound charge, that is charge that's just been moved a little bit of a distance by polarization of atoms. It's the result of bound charge and free charge, both. And as a result, sometimes the electric field is a little bit complicated to calculate because you don't know right off the bat where the bound charge is. But the displacement field is usually easy to calculate once you're given the charge distribution. Well, easy as what we did over there, okay? Whereas the electric field divergence is all the charge in the problem. Got that guy there? I just want to oh, no, I need to give you one more relationship here. The normal component of the electric field to an interface between two dielectrics changes with all of the charge, bound charge and free charge in the problem. Whereas the D field, I didn't quite get everything written in parallel here. I'm sorry about that. But it's almost working. I'm going to write the boundary conditions for the D field, which is that that's what this tells us. D1 minus D2 dot normal to the surface is 4 pi and the free charge area density, area charge density in the problem, okay? And that can make solving capacitor problems really easy, parallel plate capacitors. And then something to keep in mind. It's not something necessarily to write down, but I need to tell you this, which is that D1 minus D2 cross normal. So the components of the D field parallel to the surface are not 0, are not equal to one another on the two sides of the surface. They don't have to be. It's actually pretty clear that they don't have to be at all. Right? So that means you don't use this for the parallel component to the surface. You use the E field for the parallel component to the surface. You use, in many problems, the D field as the perpendicular component to the surface. Then you solve for the E field afterwards, and then from the difference between the two, you find out what the bound surface charge must be, which is what I'm writing here. Properties of the polarization field. And I might be missing a 4 pi here. I'm pretty sure I'm okay, but I might be missing a 4 pi. I'll put a question mark there. Divergence of the polarization field is minus rho bound. We'll work our way through those equations. I think I got it right. All right? And I've got to have a surface charge density in here somewhere.
It's a P dot.
Okay. So, this combination of boundary conditions allows you to solve most problems. Actually, I'll add to this that the potential must be continuous, right? And then this combination, if you want to keep this separate, you know, you sort of have, oh, I'm solving an E field problem without dielectric, here I am, right? That's fine. But actually, I think the combination of these two sort of all together, rather than learning first this, then that, put it all together and then you just ask yourself, do I have a dielectric or not? Anyway.
So are we going to be doing boundary problems with dielectrics?
You have one for homework. You have 2 for homework. And yes, on the examination, yes. There will be a boundary value problem with dielectrics on the exam. Actually, you've had maybe 3 for homework, boundary values with dielectrics.
1, 2.
I don't know. I'm going to say probably 3. Okay. What do so I think that I want to rewrite something to remind you as far as the boundary conditions are concerned. And then we'll take a break, and then I will
Yes,
just
3.
go into examples.
There
3.
were 3 on homework.
Okay. So that means I'm going to erase this. I'm sorry. I am. And write down some more boundary conditions. In special, not so much special cases, but I'll rewrite this. D1 minus D2. The normal component of the displacement field is 4 pi sigma free. I just want to remind you that D is epsilon E. And that's probably all that I want to write at this point. So in a couple of special cases, this is not special, this is just reminding you of something. But in the absence of free charge, which might be an uncharged dielectric sitting in an electric field, external electric field, for example. Then this simplifies to D1 minus D2 is just 0. Okay. And of course we know the curl is 0 already. So that's sufficient, right? So what I'm trying to say here is that a lot of people get all tied up in dielectrics and not dielectrics, and polarization charge and not polarization charge. But you have a relatively simple set of boundary conditions that you can apply. Right? And the thing to do when you're faced with a given problem is to just sort of start writing these down and then ask yourself how it simplifies. Right? And don't worry so much about, in fact, actually what you could do is write down the boundary conditions with dielectrics and then decide after the fact, oh, I don't need that one because it's a vacuum. Right? But I've seen students many times get into trying to figure out what the electric field is, not taking advantage of the simplicity of the displacement field. So, sort of stop, pull back from it, ask yourself whether the displacement field makes the problem easier or not. Right? Remember that the displacement field is not real. It's just a mathematical tool. What did you say?
It's a fraction of the field.
It's related to the field, and when the dielectric function is linear, then it's related to the field linearly, right? And we're only going to worry about linear functions here. In optics, you do the nonlinear coefficients. Right? But don't get all concerned about it. Just take your time, go through it. Right? Figure out what the polarization field must be, because it's the difference between the electric and the displacement fields. And then once you've got that, you can take the surface normal of the polarization field to get the bound charge, and the divergence of the polarization field to get the so bound surface charge, divergence to find the bound volume charge. Okay, so that was the speed tour of the material, and next I'll answer some questions and pick up a couple of examples. All right, that's it for now. Oh, sorry, I'm going to continue, so take a break, get some water.